Hello everyone, I am Leo Furuhata, a first-year master degree student from Tohoku University in Japan. Today, I am going to introduce our work entitled Improving the Accuracy in SpMV Implementation Selection with Machine Learning. This is the background of our research. Conventionally, high-performance computing HPC applications are optimized for their target computing system based on the experiences of programmers. The program optimization often needs to select an appropriate implementation for multiple candidates, and the implementation selection has usually been made in a try-and-error fashion. Thus, there is a demand for automating the implementation selection. Sparse matrix vector multiplication (SpMV) is an important kernel, often used in scientific computing, and there are many approaches proposed so far to accelerate its execution. In this work, CPU-COO, GPU-CSR, and GPU hybrid are used as SpMV implementations. CPU-COO calculates SpMV with CO format by CPU. GPU-CSR calculates SpMV with CSR format by GPU. GPU hybrid calculates SpMV with hybrid format with GPU. Since each storage format and processor need a different SpMV implementation, the best storage formats and processors for a matrix are different. The horizontal axis represents the sparse matrix, while the vertical axis shows the execution time. This figure shows the execution times of SpMV by 3 different SpMV implementations. As shown in this figure, the best implementation for each sparse matrix is different. Recently, it is extensively reported that machine learning models can successfully replace various tasks that have empirically been done by human experts. Chui et al. Have focused on SpMV. In this previous approach, a machine learning model learns the SpMV implementation selection as a classification problem. Their results show that using machine learning to choose the best SpMV implementation can replace humans' decision making that needs knowledge and experiences. The main disadvantage of this approach is that it does not directly consider the impact of misprediction on performance. In the case of misprediction, the performance of the selected implementation might significantly be lower than that of the best implementation. To improve the expected performance, it is important to prevent such a misprediction. As for the machine learning models, several studies have used regression models to predict the performance of HPC applications. Their evaluation results have shown that a regression model could accurately predict performance. Considering these studies, if the performance of each SpMV implementation can accurately be predicted, it might be possible to predict the best implementation as the SpMV implementation selection problem. So, in this presentation, we consider to make learn the performance differences among candidate implementations and can prevent misprediction for a matrix whose performance degrades significantly when the best implementation is not selected. For the performance prediction, one idea is to predefine the features of a matrix relevant to performance. But there are two challenges when relying on predefined matrix features. One challenge is that quantifying matrix features by a fixed number of parameters. The other is preventing information loss by the parameterization. However, it is partially known which factors significantly affect the best SpMV implementation. At least, the matrix size and the distribution of non-zero elements significantly affect the best implementation. Other factors also need to be considered to achieve high prediction accuracy. Chui et al. Have proposed using machine learning with a convolutional neural network that has feature learning capability and does not need predefined features or information loss at the SpMV implementation selection. Before explaining the proposed approach, let me introduce the previous approach proposed by Chui et al. Firstly, The previous approach converted a sparse matrix to an image. A generated image is called a feature image and used as the input image of a machine learning model for selecting the best SpMV implementation. Secondly, a machine learning model finds features for selecting the best and classifies which implementation is the best. Regarding the level for the machine learning in the previous approach, training data is composed a pair of a sparse matrix X and its ideal output vector Y. Each output vector element yi corresponding to one SpMV implementation. Yi is 1 only if the ith implementation is the best and 0 is for the others. The previous approach has the disadvantage that it can make a misprediction without considering how much the best implementation can achieve a higher performance than the others. To solve the disadvantage of the previous approach, the proposed approach aims to achieve a high performance by avoiding mispredictions when there is a large performance difference between the best and the other implementations. One appropriate solution is using a regression model. This figure shows the example of a matrix which has a large performance difference between the best and the other implementations. If the machine learning model mispredicts GPU-CSR as the best SpMV implementation, the performance impact of this misprediction is large. This slide shows the idea of how to apply regression to selecting the best SpMV implementation. To make a machine learning model learn the performance difference, it is trained to output the normalized performance of each SpMV implementation defined by this equation. In this equation, Ti and T-worst are the execution times of the ith and the slowest implementations, respectively. Applying this equation, the machine learning model is trained to produce a smaller output value for the best implementation and prevents misprediction for a matrix whose best implementation can achieve much higher performance than the others. Here, let me summarize the difference between the proposed approach and the previous approach. A big difference is using different labeling schemes to generate training data. The previous approach used Boolean value for each training data. The proposed approach uses the normalized performance value between 0 to 1. In other words, the previous approach uses a classification model to predict the best SpMV implementation. In contrast, the proposed approach uses a regression model to predict the best SpMV implementation. In this work, we compare these two approaches. This slide shows the experimental environment. Matrices are collected from the University of Florida sparse matrix collection. Then, the number of sparse matrices is increased using the data generation approach proposed by Chui et al. The number of training data and test data are 10,734 and 2,000, respectively. The system is equipped with an Intel Core i7 9700K processor and an NVIDIA RTX 2080 GPU. This slide describes the hyperparameters and the model of the previous approach experiment. Activation functions are rel and softmax. The number of epochs is 1000. Loss function is categorical cross entropy. Labeling is using Boolean values that is 0 or 1. A model is the same as that in the previous approach. This slide describes the hyperparameters and the model of the proposed approach experiment. Activation function is rel. The number of epochs is 1000. Loss function is categorical cross entropy. Labeling is using values in between 0 and 1. A machine learning model has to drop out layers installed after a 2x2 max pooling layer and fully connected layer. These hyperparameters are empirically determined based on the preliminary evaluation results. We first evaluate the proposed approach in comparison with the previous approach in terms of accuracy. The left figure shows the accuracy of the previous approach. The x-axis shows the epoch. The primary y-axis shows the accuracy, and the secondary y-axis shows the loss. The green curve represents the test loss that decreased first, but increased again from near 50th epoch. This phenomenon can be considered as the overfitting. The right figure shows the accuracy of the proposed approach. Comparing to the left figure, it is observed that the green curve, the test loss decreased consistently until the end. In other words, the proposed approach does not suffer from the overfitting problem. As a result, the proposed approach is more effective to learn the underlying rules between inputs and outputs. It proves that the regression model can fit both training data and test data. In addition to the accuracy, we used another metric named geometric mean (GM) to evaluate performance results. Geometric mean can evaluate the performance impacts of a misprediction. When the difference between Tn best and Tn chosen is small, geometric mean becomes large. When the difference between Tn best and Tn chosen is large, geometric mean becomes small. Using geometric mean, we can evaluate how much performance is degraded when a machine learning model mispredicts the best SpMV implementation. This slide shows the summary of accuracy and geometric mean evaluation results with the previous and proposed approaches. As shown in the table, the proposed approach can select the best implementation of SpMV with a higher accuracy than the previous approach. Features of sparse matrices for selecting the best implementation have been discovered through machine learning using a CNN. It is shown that the machine learning model can learn the performance ratio and predict the appropriate SpMV implementation without the need for predefining the features. Furthermore, the proposed approach achieves a higher geometric mean value than the previous approach, indicating that it can improve the selection accuracy, especially when the difference in performance between the best and the other is significant. As a result, the proposed approach can improve the accuracy and geometric mean from the previous approach by 2.35% and 1.47% respectively. This slide shows the frequency distribution of the differences in performance ratios between the optimal implementation and the selected implementation. In this figure, the horizontal axis shows the classes of the performance ratio divided into 10 ranges, while the vertical axis shows its frequency. The orange and blue bars show the result of the previous approach and the proposed approach respectively. As you can see in this figure, the proposed approach can reduce the number of mispredictions. More importantly, the number of mispredictions is reduced when there is a non-negligible performance difference between the best and selected implementation, such as these ranges. Accordingly, these results clearly show the advantage of the proposed approach over the previous one. This slide shows the conclusions of this work. Traditionally, HPC applications have been optimized for computing systems based on skilled programmers' knowledge and expertise. In this background, we extend a machine learning-based approach to improve accuracy and performance of SpMV implementation selection by considering performance ratio of each SpMV implementation. The proposed approach can improve the accuracy and geometric mean by 2.35% and 1.47% respectively. The proposed approach can select the best SpMV implementations with a higher accuracy than the previous approach, especially if the best implementation has much higher performance than the other implementations. We would like to acknowledge people who helped me on this project. That's all. Thank you for listening.